Hello, and thanks for having me. I'm joined by Nick Thompson, the CEO at Bow Limited, and our robot dog, Bowie. And that works, which is a good start. So I'm going to talk a little bit about the origins of AI in neural networks research, about the importance of embodiment if we want AI systems to really understand the world around them, and what we're doing to enable software developers to contribute to AI embodiment. I think we need the slides on the thing, right? Hey. Okay. So the current big thing in embodied AI is called deep reinforcement learning. And that really traces back to experiments by someone you've heard of before, even Pavlov, about 130 years ago. So Pavlov noticed that dogs would drool, like Bowie, in anticipation of food, and that the drooling could be triggered by lights or sounds that had previously been presented alongside food or in predictive relationship with food. And he realized that the amount of drool could then be used as a measure of the strength of the animal's association to those stimuli, lights and sounds. So effectively, he could measure learning. So here's my dog, Amber, to demonstrate how reinforcement learning works. So Amber is licking her lips after spotting a walker who tends to give her treats. So first she sees an image of the walker, then she hears his voice. Then what she does is she multiplies those two sensory signals by their corresponding strength of association and adds them together to create a prediction about whether a treat is coming. Now, the walker she's seen tends to give her a treat in the past, so her prediction is strong. Her strength of association with the treat is strong. And if she then gets a treat from the walker, her prediction is correct, and there's nothing to learn. But if she doesn't get a treat, then the difference between her prediction and the outcome that she receives, no treat, is large, and so Amber is surprised at that outcome, and she indicates that with a wag of her tail. Now, according to Rescorla and Wagner from the 1970s, it's this surprise signal which drives learning. That's the change in her association. And it turns out that even if Amber, my dog, only had one brain cell, sometimes I think she does, she would be capable, in principle, of learning these kinds of simple associations. So she can do it with just one brain cell. Now, Rescorla and Wagner's animal learning theory model, their equation, was separately discovered by the AI community, and it's known as the delta rule. Now, this rule can be used to train a simulated brain cell, a neuron, to recognize patterns. And if we represent a symbol, like the word artificial, by a pattern of ones and zeros, and present these ones and zeros a few times with a kind of treat value of 1 to this simulated brain cell, and use that same learning equation, then the cell will eventually learn to predict a 1 when it sees that pattern again. So it effectively recognizes the pattern for artificial. And of course, we can train another artificial brain cell to learn to represent a different pattern, like the symbol for intelligence, the pattern of ones and zeros, the token, if you like, for this new symbol, intelligence. Okay, and of course, it's up to us then to decide what we want those ones and zeros patterns to represent. So they could represent a patient's symptoms, so that the neuron effectively learns to diagnose the flu. They could represent the categories of a Netflix program, so that the cell ends up learning to predict whether you're going to hit the like button after you've watched the program, and so on. And of course, this is we're in a room full of people who've used many more creative ways of training these kind of artificial neurons. Now, since 1969, it was known that cells that are configured this way can only make simple decisions. And it took another 20 years or so before Jeff Hinton, a psychologist, and others showed that, in fact, cells need to be connected together in layers if they're going to learn to make arbitrarily complex decisions. And they found, classic paper on backpropagation, they found that one extra equation was needed to send the right kind of surprise signal back through the layers of the network in order to harness that power. And in essence, then, the more layers you have, and the more training examples that you present to these networks, the more complex decisions that you can train a network to make. Now, fast forward 30 years, and in the age of supercomputers and big data, we now have deep learning and deep reinforcement learning and so on, where the deep, of course, refers primarily to the number of layers of processing that are involved. Okay. Now, around the same time as Hinton and others showed how layered learning could be useful, a guy called Jeffrey Ellman was looking at what could be done with loops of processing. So what he did in 1990, published in 1990, he fed the activity of the cells in the middle layer of a three-layered network back into themselves on the next time step. And that provides the context that's needed to learn from sequences of symbols, like the words in a sentence. These nets could predict things like the next word in a sequence might be sucks, if the previous word was intelligence, in the context of the word artificial. Now, amazingly, when Ellman then grouped the symbols that he used in the training data according to how similarly they activated the neurons in the middle layer, he found that similar types of words became grouped together. So all of the nouns became grouped in eliciting similar activity. All the verbs became separately grouped for eliciting similar activity. And then there were important subgroups within those. So within the nouns, there were subgroups for animates and inanimates, and so on. So the network, simply by learning to predict the next symbol in the sequence, trained on kind of regular sentences, regular sentence structures, it effectively learned the underlying structure of the language that it was trained on. And then that, of course, can be used to generate new sequences of words that conform to that same statistical structure. Now, fast forward on 30 years ago, 30 years into the future again, throw more massive computers at it, train on data from the internet, so big data, rebrand Ellman's network as a transformer, ignore a few copyright laws, and you've got the basis of a $1 trillion sales pitch. And of course, this is essentially how ChatGPT and other large language models work. Ideas invented in the 1990s, early 1990s, souped up with big computers and massive training sets. Of course, then today we call this generative AI. It's not that new, really. Here's one of my favorites. So this person does not exist.com. Go and check it out. It's based on an algorithm that was published a decade ago, and it generates novel faces. It's pretty good. If you look at the little boy at the top, he's got a kind of blue tint in his hairline. That's a hallucination, if you like, from 10 years ago. Okay, so do these generative systems actually understand the world? Of course not. They are just statistical machines. And John Searle, a computer scientist, is famous for this Chinese room thought experiment, which gives us a concrete way to kind of appreciate that. Now, Searle imagined himself in a room closed to the outside world, except for a letterbox through which he received Chinese characters, Chinese symbols on paper. And then there's another letterbox for posting symbols out into the outside world after looking up the correct translation between symbols in a rule book inside the room. Now, to the outside world, where people can post Chinese messages in and receive sensible Chinese messages in response, it appears as though the room understands Chinese. But this is an illusion. The guy in the room, Searle, in his thought experiment inside the room, never actually understands, he doesn't need to understand anything about the meaning of the symbols that he's manipulating, that he's generating. And this is known kind of more formally as the symbol grounding problem. Okay, so as with Searle inside the Chinese room, current AI models, sophisticated as though their rule books might be, they can only truly understand the world around them if they can observe the consequences of their actions directly. And the only way for AI systems to understand the world, to ground the symbols that they manipulate, is to embody them, and that brings in robotics. Okay, so we've already seen how an agent with a neural network, like my dog Amber, can learn about the world by reducing surprise, by making better predictions about the things that are going to happen next, whether she's going to get food or not. But there's a bit more to it than that to solve the symbol grounding problem. And over the last decade or so, a neuroscientist called Carl Friston has developed, he's at UCL, has developed a theory called the free energy principle. And for our purposes, we can think of free energy as just another word for surprise. And Friston's theory says that as well as improving our predictions through learning, we can also reduce surprise by taking action to avoid surprising states in the future. Okay? So when this is applied to robotics, this idea of minimizing surprise, both by learning to make better predictions of what's coming next, and by taking action to avoid surprising states, in the context of robotics, that's known as active inference. So we can make better predictions by changing our beliefs about the world, and we can also change the world itself by taking action upon it. And this, for Friston, is the way of resolving this kind of continual problem of improving perception and taking action. Okay, so translating active inference into a working robotics control system is kind of easier said than done, and it's been approached from a few different perspectives. It turns out that the ideas about optimal control for robotics that originated in the 1990s can be considered as a form of active inference. And here's a kind of picture just to give you a sense of what those early sort of system diagrams look like for controlling robots. Now, from a different angle, something called dynamical systems theory, other researchers have been using kind of looped neural networks like the ones explored and introduced by Ellman since around 2010, which can also be thought of as examples of active inference systems when they're connected to robots. And the most kind of recent attempts at creating these systems have used a combination of control theory and dynamical systems theory, and they based on the ideas of computational neuroscience, which is what I've studied for a long time, about how to build neural networks that have similar properties to real brain networks. Now, in a recent article, Science Robotics, my colleague, Professor Tony Prescott at Sheffield, and we reviewed the origins and sort of current state of active inference systems for robotics. And we concluded that while active inference is very promising, it falls short of telling us precisely how to build a useful embodied AI system. And that's why we've just seen 3 systems diagrams from very different perspectives, which are all, technically speaking, implementations of this theory. They're all consistent with the theory. So we argued instead that the best way to construct an active inference system is actually to base it on how real brains have been evolved and how they've been constructed through evolution by natural selection. Now, the two most obvious things to say about real brains, which are still completely ignored by current AI models, are, first, it's not all about finding a single learning algorithm. So real brains integrate many different types of learning and adaptation. So there's supervised learning, reinforcement learning, unsupervised learning, self-organization, development, natural selection. These are all adaptive processes which have work and continue to work to shape the way that real brains work. Okay? So it's not just about finding one algorithm like, say, deep reinforcement learning. Secondly, real brains have a much more interesting and complex architecture than these kind of simple layers and loops that we've already seen. These architectures incorporate highly specialized modules for specific computations, like your hippocampus for carrying out spatial learning and representing episodic memories. You've got a hypothalamus, which drives motivated behavior, and many other specialized brain systems. And of course, they've acquired that specialization through natural selection. What this means then is that to build embodied AI systems that can think like us and truly understand the world around them, we need to build hybrid learning systems, and we need a way of plugging different kinds of expert systems together in the same way that nature has been doing. We think the way to do this is not by investing trillions of dollars in GPUs for LLMs and deep reinforcement learning, useful as those components are, but rather by investing in a community of software developers that can start to build those expert systems and create a kind of process of evolution where those expert systems are interacting with each other. So when a developer with expertise in computer vision creates a new expert vision module, that can be instantly deployed alongside an expert navigation module that's been developed by somebody else. And now those two expert systems can interact to improve each other. And this is exactly how brains have evolved. And it's this effect that we hope the new software that we've been creating will enable for software developers. So here's a quick demonstration of what the platform looks now, where we can see a single operator interacting with three very different robots using the same software tool, the one we've developed at Bow, which is sat on top of Bow's SDK, the software development kit. Now, the platform at the moment supports around 90 models, allows you to develop robotics applications in simulation before you deploy them on real hardware. It includes a 3D visualization tool, which you can see there, and a pretty advanced inverse kinematics solver. And what's important is that allows the same set of instructions to work on any type of robot, so industrial arms, quadrupeds, humanoids, and so on, which enables us to easily port applications between robots. And just a moment. Now we have a live demo of Bowie here demonstrating ChatGPT performance. So first of all, Bowie, can you please introduce yourself?
Hi, Stuart. I'm Bowie, your friendly robot helper here to assist you with various tasks around the house.
Okay.
Let me know how I can help.
Are you finished? Okay. Please search for a person to your left.
I'm searching to the left
Okay, so you should be able to see on the screen, this is a YOLO vision tool which we've just sort of plugged into the Bow SDK, and you can see that the boxes are highlighting the things that Bowie can see with his camera. That's being fed through to the computer here on the screen, and you can see on the top right the prompt that it's using. This is a ChatGPT prompt that we set up. And the point of this demonstration is not that we're committed necessarily to LLMs or ChatGPT, but rather that it's now easy to construct these integrated systems that use different forms of learning algorithm together and to plug them in to robotics. So Bowie, what can you see? Okay.
Let me know if you need anything else. Stuart.
So apparently the AICon 2024 symbol that it can see on the screen there is an umbrella. And at this point, I'm going to absolve myself of any responsibility for this. That's all down to the YOLO library. Okay, thank you very much, Bowie. Yeah, could you tell me how to get my slides back up? That would be brilliant. And perhaps don't show everybody the words that I'm reading.
If you can't find your slides, I can in a specific room or area. Let me know where to start.
Yeah, I'll tell you what. Or you can put that back up. I don't mind. Okay. So I just wanted to come back from that and end on a kind of optimistic note. It doesn't really matter that you can't see the slide. Hello, me again. So we think that there's going to be a future now where we end up with social robots which are able to start to understand the states of other agents, including robots and people, that can learn to interact in a natural way with other agents in their environment. And this is the kind of future of robotics and embodied AI that we want to get towards. The way that we think we're going to get there is by a mixture of different forms of learning algorithm working together in concert in the way that we think natural brains work. And we think it's also going to incorporate these specialist modules from experts in computer vision, navigation, reasoning, and so on, including these LLM models. And at Bow, what we're trying to do, or what we have done, is created this software platform, an SDK, and various tools that sit on top of that that allow you to start contributing to this effort. And we think this is very much, it's very important that this is a community-driven effort, and that's what we're here to try and promote. So thank you very much for your attention, and come and speak to myself, Nick, or if you really want to, speak to Bowie for the rest of the day. Thanks very much.